All right, we are going to start a second video for 5.5, and this one's going to be related around 5.5a. And the trig equations that we're going to be focusing on today are going to be ones that fall underneath this category that's listed right here. So equations that may need some factoring or possibly some simplification first. So those are the two main ideas that are in this. Or we might actually have more than one trig function that's associated with the question in itself. So we might have a situation where we're dealing with maybe a sine and a cosine that both need to be solved in those regards. All right. So these still fall under the idea of what I would call type 1 kinds of ideas, mainly because they're relatively easy to factor. There's really not a whole lot of new things that are here, but just the fact that they've gotten a little tiny bit more complicated is what's going on. Now, this very first question that we see at the beginning here is a really good example of a question that's already been completely factored down. And just to go back to remind ourselves that when we end up getting factored binomials like x plus 3 and then we get x minus 5, we end up setting that idea equal to 0 and solving for each one of the individual roots, being that this one will be like negative 3 and this one would be 5. This particular concept here is no different than that same idea. We're basically going to solve these two individual trig functions separately, and we're going to get an answer for each one. So this one's going to be a cosine of x is equal to 1, and this is going to be a sine of x is equal to negative 1. And each one of those is going to generate its own individual answers. And cosine is 1, if I'm kind of thinking about the unit circle, its x is going to be 1 over here at 0. So x is 0 for one of those. And then when is it going to be negative 1 for y? And that's going to be when x is equal to 3 pi over 2 when it's going down here. And each one of those, again, written as their all function. So it's not really like I can actually make these two fall on top of one another. So each one of these is going to be written individually as 0 plus 2 pi k, and x is going to equal 3 pi over 2 plus 2 pi k. Now, the real thing that's being stated here that you really need to understand is that we're going to separate the work here, and we're going to get solutions for either one, because either one of those particular topics could have turned to 0 and caused the actual multiplication between the two to become 0. So it's like technically finding roots is what's going on here. Now that one was nicely factored. They don't have to always be that particular kind of idea. They could possibly be, factored like number 2, where it has something that's been pulled out here. We would take something like cosine of x. This one would be cosine of x is equal to 0. Could be the outside. Or it could be that we're dealing with this guy, which is that cotangent of x is equal to 1. Now, kind of thinking about each one of those, when is cosine 0? Cosine happens to be 0 at pi over 2 and happens to be 0 at 3 pi over 2. So there's two of those that are listed. And cotangent of x is equal to 1. If I did the reciprocal and turn this into tangent of x, it would still be 1. And that ultimate answer would give you a yielding of pi over 4 and 5 pi over 4. Because this happens in both, if I'm thinking about ASTC, it happens in both the first and the third quadrants. Now, as I start to kind of draw these, and it's probably well worth to see all the different ones going in each direction, we've got up here pi over 2 and 3 pi over 2, 3 pi over 2. And then pi over 4 is listed here along this axis, and 5 pi over 4 is listed down here. You're going to probably be able to pick up at least 2 of them in one successive all solution. So I would expect that we would take pi over 2 and add pi k to it, so that we'd end up generating the top and the bottom ones that go together. And this one would be x is equal to pi over 4 plus pi k as well too, because we can catch this first one and then rotate a pi amount to get the 5 pi over 4. Okay? You need to kind of draw these separate little pictures here to kind of try and see whether or not there are ways to be generating all of them or some of them at the same time. Okay? Now, factored out. That one had a GCF pullout. Here's where the whole kind of idea has been pushed together into what I would say a factored form. Now again, one of our goals here is to factor it, and if we see that kind of question, we could also see it like 4x minus 1 is equal to 0, and you could see that that definitely would be a difference of squares, like 2x plus 1 and 2x minus 1, and that whole concept or pattern recognition is going to be the exact same thing that we're going to basically see down here. This will turn into 2 sine x minus or plus 1 and 2 sine x minus 1. Now each one of those individually needs to be solved, or better yet, when is sine x equal to negative 1/2 and when is sine x equal to positive 1/2. And if I'm thinking about sine as 1, 2, 3, ultimately the only time it's going to be 1 is any pi over 6 location, and it's going to be positive based on ASTC in the first and second quadrants. So this answer would be pi over 6 and 5 pi over 6. And this one would be the negative answers, which are in the third and fourth quadrant, or 7 pi over 6 and 11 pi over 6. Now every single one of those pi over 6 locations can definitely be written as coordinates that we can reach in, now I'm writing these relatively shallow because they do have a reference angle of only 30 degrees, okay? This one and this one are a pi distance away from each other, and this one are a pi distance from each other. So we could really write it as x is equal to pi over 6 plus pi k, and the other one would be from the second quadrant, or x is equal to 5 pi over 6 plus pi k. I try my best to pick the very first utterance of the solutions and then add on my recursive amount after that. So I try to pick anything that's in the first or second quadrant ahead of time, even though it really technically doesn't matter as you rotate the actual axis based on the pi k's. Okay. Now, as we move down here, we're just going to see a lot more factoring basic concepts that are in here. Some people will make mistakes right out of the gate and look at that kind of guy right there, be like, oh, that's a double angle. Double angles don't really probably offer you as much as you possibly would hope for. What you really need to see here is that there's a cosine and a cosine, and you should yank that kind of concept out based on GCF. That would be 2 sine x down here on the end, 1 plus 2 sine x, and this is all set equal to 0. Again, we're solving as several answers here. Cosine is 0, and sine of x is equal to negative 1/2. Solving for all the individual solutions here, cosine is 0 at pi over 2 and 3 pi over 2, and sine is going to be there at, we did that one just a second ago, 7 pi over 6 and 11 pi over 6. Now your first gut instinct is to probably see that maybe these guys don't have anything in common, but it is definitely worth drawing their locations to really see whether or not they have a connection to each other. So pi over 2 and 3 pi over 2 definitely listed here and here. And then it's funny to see that the 7 pi over 6 and the 11 pi over 6 are in these locations, and it does make a concept that I might be able to catch all three of those in one felled swoop. And you can see, if I thought about this one as 7 pi over 6 and 11 pi over 6, this is 3 pi over 6, and the distance between 3 pi over 6 and 7 pi is 4 pi over 6, and from 7 to 11 is 4 pi over 6. So you could really say that one of the solutions is pi over 2 plus 4 pi over 6 is the location of distance that's going on here, or better yet, 2 pi over 3k. That could be the solution that would solve for these three, and then the other one would be this 3 pi over 2 that we would want to catch every single time, 3 pi over 2 plus 2 pi k. And, or you could even say it was just plus pi k, but it would just ultimately overlap the pi over 2 in the first place anyways. We'd catch that one in the first one also. So it kind of depends on what you want to put right there, if it's 2 pi k or pi k, okay? But the goal there is draw yourself a picture and really look for those possible common difference values that are in between certain ones, and you can pick them all up in the all solution. Now, just like in factoring concepts that we've seen in the past, moving things to the left-hand side is completely feasible here. It wasn't feasible when we did verifications, but in solving, it's totally reasonable. I'm going to take that value out at exactly the same time, and I'd end up with sine x minus 1 is equal to 0. So it moved over there, and I think there's supposed to be a plus sign. Oh, no, I subtracted it over there. That's where the negative came from. And now I'm dealing with cotangent squared x is equal to 0. So that's one of the solutions I have to solve, and the other one is sine x is equal to 1. Now I'll avoid that one for a second because I got to think about it. Sine is 1, so that's going to end up being pi over 2. Boy, your time's up, G. Now you got to figure out how to do that other one. Cotangent squared being equal to 0 would ultimately be where the cotangent function is 0, and that would ultimately be at pi over 2 and at 3 pi over 2. And the way I was thinking about that was specifically I was thinking about the shape of the cotangent function, and the shape of the cotangent function is that it has asymptotes at 0 and at pi. It's been a while since we've seen that one. And it comes down here and crosses the axis at pi over 2. So that's when it's going to be ultimately a 0 value. And that also happens again at 3 pi over 2 because we're going to 2 pi. Now, we could catch all of these answers. What you're going to want to basically look at is that pi over 2 is going to be one of the solutions for darn sure. And then we're going to catch the next one, which is going to be a pi k away. And that'll be your all solution for that particular case. So it's okay for you to move things to the other side, set your values equal to 0. That would be a very similar case that you would be dealing with in, say, number 7, the one that's right directly below that one. You're basically going to get a tan squared x minus tan x is equal to 0. You're able to pull the tan x out of that and get tan x minus 1 on that guy. And you'd be able to solve for each one of those individual values. Now let's solve this guy real quick here. When is tangent of x going to be equal to 0? Well, that's going to happen when sine up above is 0, sine over cosine. So ultimately that would mean that it's got to happen at pi or 0 and at pi. Those are the two solutions. And when is tangent of x going to equal 1? Well, based on ASTC, it's still got to be positive. It's got to be in the first and third quadrant, and that happens at pi over 4 and happens at 5 pi over 4. So there's your two solutions there. Now, are we going to be able to pick all those up? Yeah, probably not. 0 and pi are on either side. Those ones are, I think we're going to probably go with 0 plus pi k as one of the answers. And the other answer is going to end up being pi over 4 plus pi k in the other regard. Okay? So ultimately, the factoring and GCF stuff is probably nothing that's really super surprising. Now, what I do want to point out is as I move further into like number 6 and number 8 here, these are, in effect, really trinomials. And if you can't see it right out of the gate there, it is well worth trying to look at it like it's good old-fashioned Algebra 2 concept about what it's factored to. Now, a lot of people are still stuck in the world of front times back and make that magic x and so forth. You kind of should be at a level now where you could probably generate a set of binomials that would multiply to be that. 2x and x would make the 2x squared. This has got to be a 1 and a 1. What I'm doing here is good old-fashioned guess and check to make sure that I get it. It's got to be a negative in the middle, so I'd ultimately make the negative 2x there and the positive x here, and there's your two basic functions. Now, that's not what it is. It's really supposed to be with cosines. The answer here is 2 cosine x plus 1, and cosine of x is equal to 1, or minus 1. And I'll solve each one of those. Cosine of x is equal to negative 1/2, and cosine of x is equal to 1. And we'll get solutions for each one of those. Cosine of x equaling 1 happens at 0. And cosine is negative. Let's take a look at that. That's cosine is 3 to 1. I keep drawing an S. I don't know why. Cosine is 3, 2, 1. So the answer must be a pi over 3 reference angle, but based on ASTC, I would definitely say it's going to be negative in the second and in the third. So the answer would be 2 pi over 3 and 4 pi over 3. Now, those particular locations, 0 over here, 2 pi over 3, which is up there, and 4 pi over 3, which is down here, you can probably tell that all three of those could be reached in one fell swoop. And that's another one of those 2/3 concepts. Maybe if you've ever taken chemistry, you know, we're talking about things like a tetrahedron right there. The 120-degree angle is what I'm talking about. And that would be x is equal to 0 plus 2 pi over 3k, and that would pick up all three of them at exactly the same time. All right? So, pretty straightforward. Now, I'm not going to disregard the idea that front times back stuff is doable. I'm looking at that quadratic, right, or polynomial, and I'm basically saying, well, let's try it. Front times back is negative 12, and it has to generate the number 1 in between. It must be number 4 and negative 3. You could do your grouping method in between there, so you're like talking 6x squared plus 4x minus 3x minus 2. This is why you passed Algebra 2, because you can do these things. 2x times 3x plus 2, and this one would be a negative 1 that I'm going to take out. That's 3x plus 2 as well again. And I've got two new answers, and that is 2 sine x minus 1, which is one of the polynomials, and the other one is 3 sine x plus 2 is going to be the other polynomial, and those are both set equal to 0. Now, some of these will actually make a Pythagorean unit circle one. Like this one makes sine x is equal to 1/2. And you're like, oh, sine is 1, 2, 3, and it's positive in the first and second. So it must be pi over 6 and 5 pi over 6. There's your two individual answers for that one. Now, that's two of the answers. This one makes a sine x that's equal to negative 2/3, and that is not unit circle. And what we're going to be basically relying on here is ASTC to tell us where the inverse is really going to see this question. And the inverse sign that you're going to get out of this is going to see the negative in the, since sine exists in the first and the fourth, the negative is going to see this in the fourth quadrant. So I'm going to go the inverse sine of negative 2/3, and it's going to give me a negative radian that's in the fourth quadrant. Again, probably not the best answer because it's going the wrong way. It's going clockwise rather than counter. I'm going to add 2 pi to this. So I'm going to add 2 pi and get the full angle going in the positive direction, the way we like it. So one of the answers is going to be 5.55, and that's the one that's in the fourth quadrant. The other one is going to be in the third quadrant, because it's negative, and that answer is going to still have the same reference angle that we just got on that calculator, but it's going to be this amount beyond pi, so I'd be like second pi added to this answer, which is the reference angle, but I'm not going to use it as its negative. I'm going to use it as a positive, so I go beyond the pi value, and I'll end up with a second answer of 3.87 in the other location. Now, the all solutions on these, I don't know if the two of them overlap one another. I bet you they don't. I don't think they probably do. So you're going to be basically stuck with pi over 6 plus 2 pi k, and 5 pi over 6 plus 2 pi k, and 3.87 plus 2 pi k, and your last but not least 5.55 plus 2 pi k. I don't think there's any relationship of the angles. You relatively won't find relationships between unit circle ones and ones that are gathered by an inverse in the long run. It might be possible sometimes to get these inverse ones. Specifically, they're probably in the second or fourth, or maybe the first and the third. Then you might be able to pull off some kind of shortened all answer in those particular cases. All right, now, basic idea that we just discussed there. You're going to run into questions that might need factoring. I don't think you're scared about that. There are going to be questions that involve taking out a GCF. Again, probably not a scary idea. And more than anything, you might run into difference of squares concept, or you have to move something from one side to the other. But in general, the only reason why these questions are even in the second day is because they truly end up having more than one function that's associated with them, so you end up with more possible solutions. Okay? Keep working on these. Really, the only way to keep getting good at them is to keep practicing, keep doing your homework, checking your answers against your answer documents, and then we will push on to 5.5b tomorrow. Bye.